Okay, let's get this started. Hope my voice is picking up on the camera good enough. If not, oh well, doing the best I can. This is the lesson that would have been taught on Monday, November 19th, the Monday of Thanksgiving week in college algebra. So let's go through the section. And I'm assuming that by the time you see this video, we'll have already completed both sections 3.1 and 3.2, and we're moving on to 3.3. As the title says up on the screen, this section is about polynomial division. And just to put it in the context of why we're doing this, relative to what we've previously done, in section 3.2, we graphed polynomial functions. We graphed polynomial functions. Yeah. And when we graphed them, we found a variety of information before we drew the graph. Specifically, we found end behavior. And that was easier when unfactored. If the polynomial function was factored, you can get the end behavior. You just have to ask yourself, what would the leading term be? And then use its leading coefficient and the degree to determine what the ends of the graph would do. And we also found the y-intercept. Sorry, functions there. You know, I'm a grammar geek. The y-intercept was easy because you just find f of 0. Plug 0 into your function, and what you get out is your y-intercept. And we also found the x-intercepts. And remember, that also incorporated multiplicity. So plural would be multiplicities. And that told you whether or not the graph crossed the x-axis or touched the x-axis and turned around. This is easier when factored. So the three things that we looked at, what do the ends do, what's the y-intercept, and what's the x-intercept? End behavior is not too hard to do, assuming that you know what the leading term is. And even if it's factored, you can imagine the leading term without multiplying it all out. Finding the y-intercept is just a matter of plugging in 0, so that's also pretty easy. Finding the x-intercepts is easy when it's factored, but if it's not factored, it can be a nightmare. For example, if I ask you to find the x-intercepts of f of x equals, let's make it easy, parentheses x minus 1, parentheses x minus 2, parentheses x minus 3. That's easy because it's already factored. Remember, to find the x-intercepts, you solve your function equals 0. And if it's factored, that means you just put each factor equal to 0. And then solve each smaller equation. So you would get 1, you would get 2, and you would get 3. So it's easy if it's factored because you want it factored, and if it's not factored, it's not so easy. Compare it to this versus, let's say I ask you to find the x-intercepts of this one. And by the way, before I even continue, in my opinion, the best thing you can do with this video is watch it. If you're treating it like class and trying to write down everything that I'm writing down, you may miss some of the things that happen. So treat this more like a TV show than a lesson that you're frantically writing notes for. And if you insist on writing notes, watch the video again and then write your notes. Alright, so let's say I ask you to find the x-intercepts of this one. F of x equals, and this will take me a second to build. We'll start with an x cubed minus 6x squared. This is where I have to slow down for a second, so forgive me as I think out loud. 6 plus 3 plus 2 is 11. so plus 11x. And for the last number, minus 6. And again, this is not factored. Well, if I'm going to find the x-intercepts, I have to solve x cubed minus 6x squared plus 11x minus 6 equals 0. And this is where we kind of run into a problem. In the previous example, it was already factored, so we could split the equation right now. In order to continue this current example, you have to factor this. Now, I know some of you are really good at factoring, and you're probably already trying to factor this by grouping. I'll tell you right now, this will not factor as a grouping problem. Because if you try it, alright, I'm going to have to go in the hall and exercise my right to tell people to keep their mouths shut. I'm busy here. Anyway, if you try to factor this by grouping, you take out an x squared from the first two and get x minus 6. But what would you take out from the second group? The greatest common factor is 1. And if you factor out a 1, you're left with 11x minus 6. And the problem is these don't match. But if you're going to factor by grouping, they have to. So what does that mean? That means if you're going to factor this, you're not going to do it this way. It's not a grouping problem. That doesn't mean you can't factor it. That just means you need a different way to factor it. So the question is, how do you factor it? And the answer is you use polynomial division. Forgive the sloppiness, but you're used to it by now. I'm going to show you a technique that will factor anything. And because it's a universal technique, it's a little more cumbersome. But once you get it down, man, does it make life easier when it comes to solving these things. So let me go to a new page. And my next objective is to show you how to perform polynomial division. There's two ways to do it, depending upon what you're dividing by. Let's look at the homework and see what happens on the first question. First question says divide this. Not a problem. Divide again, a little chunkier, but the technique's going to be the same. And notice how it's asking for the answer here, something plus a fraction. In the previous problem, it also gave you something but plus a fraction. So we're going to be doing some division problems, getting a quotient and getting a remainder and putting the remainder on top of the fraction. In fact, let's take this first one. So this is similar to number 1 in the 3.3 homework. Give me a second to transfer it over here. 14519. For example, divide x squared plus 4x plus 5 divided by x plus 9. And you may have heard me just a second ago say 14519. I was trying to remember the coefficients. 1, 4, 5, 1, 9. I think I said that. That's what I meant to say. Because I know where the x's go. I just needed the coefficients. There's two ways to do polynomial division. One always works and it's cumbersome. The other one doesn't always work, but it's much quicker. The way that always works is called long division. This is where you roll your eyes and complain about long division being long and stuff like that. Get over it and move forward. I'm not sure what's going on across the hall. Maybe I didn't pick the best room to film this in. Anyway, the trick to doing long division with polynomials is to ask yourself, what would I do if I were doing a number long division problem? For example, I'm going to compare this to an unrelated division problem. Let's say 297 divided by 12. Because if you know how to do this division problem with numbers, and you better, then you really know how to do this one. You just have to alter how you ask the questions. For example, the first question you would ask yourself with the number division problem is how many times does 12 go into 29? And you would say 2. You ask the same question with the polynomial with a couple of exceptions. Exception number 1, you only look at the leading terms and then ask yourself how many times does x go into x squared? The problem is, that's a weird question. How many times does x go into x squared? There's a way to answer it really easily, and of course I didn't leave room to write what I wanted to write. So give me a second as I do a little bit of cutting and pasting, or moving rather. Of course it's rain, but it's going to rain anyway. Alright, so to answer the question, how many times does x go into x squared? Take what you're dividing into, the x squared, and divide it by the piece on the outside. Of course, I need to tell you the vocabulary, a little bit too late, but better late than never. The piece that's on the outside of the division problem is called the dividend. The piece that's on the inside is called the, and of course I wrote that wrong. Wow, I'm doing awesome tonight. Let's try this one more time. The piece you're dividing by is called the divisor. Sorry about that. The piece you're dividing into is called the dividend. And the answer that you're going to get, which I'm building, is called the quotient. I will be using those words quite a bit. Okay, but let's get back to the polynomial division problem. You divide the leading term of the dividend by the leading term of the divisor and basically reduce it. When you reduce x squared over x, you get just an x. Alright, so the move here is similar to the move with the numbers. How many times does 12 go into 29? How many times does x go into x squared? Divide it, write it out. Now let's go back to the number problem. After you figure out what goes on top, you multiply it times the divisor and write it underneath the dividend. And again, I'm assuming you know this. 2 times 12 is 24. You do the exact same thing over here with polynomials, except it's more of a distributive thing. Multiply the x times the entire divisor, including the 9. And then whatever you get when you multiply those goes underneath the dividend. So x times x is x squared. X times positive 9 is positive 9x. Notice I said positive 9. You want to be very careful to keep track of all your signs in long division. Alright, let's go back to the number problem. Once you multiply with the 24, your next move is to subtract it. 29 minus 24 is 5. Same move over here, but you're going to subtract this entire x squared minus 9x. Excuse me, x squared plus 9x. Since you're subtracting it, you have to change the sign on every term. So when you come over here to subtract, change all your signs and then add, or rather combine is a better word. So I'm going to write change signs and combine. I'm subtracting, but change signs and combine has a little more oomph. What should happen is these leading terms should cancel, and then the next term should do whatever. In this case, they combine to get negative 5x. So it's the same moves, just in a slightly weirder setting. Go back to the number one. After you subtract, you bring down the 7. Over here, after you subtract, you bring down the next term, which is a plus 5. And then you can do it all over again. So back over here with the numbers. How many times is 12 going to 57? The answer is 4. Over here, how many times is x going to negative 5x? Again, if you're having trouble seeing that that's negative 5, take what you're dividing into, put it on top of what you're dividing by, and reduce it. If you reduce negative 5 over x, you get negative 5. I'm sorry, if you reduce negative 5x over x, you get negative 5. And remember, after you write something on top, then you multiply. So in this problem, it would be 4 times 12 is 48. And in this problem, it would be negative 5 times everything over here. Watch your signs. Negative 5 times x is negative 5x. Negative 5 times positive 9 is negative 45. Oops, getting ahead of myself. Over here, subtract, and you get, looks like 9. And over here, if you subtract, you really change the signs and combine. So since this is negative, it changes to positive. And since this is negative, it changes to positive. These cancel. That's why you do what you do to make them cancel. Over here, you get plus 50. Alright. At that point, the division's over because there's nothing else to bring down. The only thing that's left is how to write your answer. Over here on the number problem, there's a variety of ways to write the answer. The quotient is 24, and all of you should know that this number down here is the remainder. How are we going to represent the remainder? We could use decimals here, but we're not going to because we can't over here. We could put R9, that's kind of lame. Or you could put 9 over 12 and add it on to the answer. Now, I know 9 over 12 reduces, and it's driving me nuts to not reduce it, so I'm going to. But the point I'm making is that you put the remainder on top of the divisor and add it to your quotient. That's how we're going to do it with polynomials. You're going to take your quotient and add to it your remainder over your divisor. So in the homework, it's expecting you to type in an answer similar to that. X minus 5 for the quotient, 50 for the remainder. X minus 5, 50. Ta-da! Notice that it already gave me the denominator of that fraction. How convenient. The same thing happens. Excuse me. Same thing happens with the rest of these. When the numbers get bigger, you just have to be a little bit more careful. The impact of having a 3 in front of this x is when you have a 3 over here and you're dividing, that just means you have numbers that you have to clean up. I think most of these problems are designed so that when you set up this fraction, it will reduce to a non-fraction. Just be consistent and you should be okay. There are a couple of other things I need to point out about long division before I move on to the other type of division. Let me see if I can find a problem that does it. Didn't take long. This one actually has two issues. The first issue is the fact that there's an x squared in the bottom, which really doesn't change your plan of attack. But the more subtle issue is there are missing pieces in these problems. For example, when you have an x squared, you expect to see an x next. There's no x term. And on the top, x to the fourth, x to the third, x squared. I'm missing the x and the constant term at the end. If you have a long division problem with missing terms, you have to represent them with zeros. Give me a second to tweak these windows so that I can see the Digimemo pad and the homework problem at the same time. So just a little bit of finagling here. Alright. Let me write this homework problem. This is based off of number 3 on homework. Okay. So for example. And notice that this division problem is written as a fraction. That's okay. A fraction is a division problem. The sooner you accept that and move on, the better your life will be. That all fractions are just division problems. Okay, now that I got that, here's what I mean by missing terms. When you have a polynomial written in standard form, the highest term is in front, the one with the degree, if you will, and then every power after that is represented. Well, there's an x squared, but there's no x term here. There's a constant term at the end. Remember, a constant term has no x on it. On the top, if the degree is 4, I expect x to the fourth, x to the third, x squared, x, and then a constant. So at the top, there's no x term, and there's no constant. Why does that matter? Well, when you set up a division problem, you have to have every missing term represented, and the way you represent it is with a 0 power. So this is going to be a long division problem. For the divisor, it does start with 3x squared, but since there's no x term, I have to write it plus 0x, and then the plus 1. And then in the dividend, 21x to the fourth, plus 3x to the third, minus 5x squared. And again, there's no constant, there's no x term, no linear term, so I have to write it plus 0x, and there's no constant, no number without an x, so I even have to write it plus 0. The reason you have to provide the missing pieces is so that when you go through long division, your like terms are guaranteed to line up. All right, I'm going to go through this one a little bit faster for the sake of moving on. So here we go. Start by dividing the leading term into the leading term. Ask yourself how many times is 3x squared going to 21x to the fourth. If you don't know, set up that fraction. I got room right here. 21x to the fourth divided by 3x squared. If you reduce that as 7x squared, that tells you the first term in your quotient. Then multiply. It's going to get distributed 3 times. 7x squared times 3x squared is 21x to the fourth. These should match so that they'll cancel when we subtract. For the next term, 7x squared times 0x is 0x to the third. And then the third term, 7x squared times positive 1 is positive 7x squared. Then subtract, and remember when you subtract, you change the signs and combine. So change this to negative, change that to negative, which is kind of silly because it's 0, and change that to negative, then combine. These cancel like they're supposed to. Your x cubes combine to give positive 3x cubed. Your x squareds combine to give negative 12x squared. Then you bring down the next term, and then you do it all over again. Remember, when you divide, at this point you only divide into the leading terms. How many times is 3x squared going to 3x cubed? Again, if you can't see the answer to that, put the positive 3x cubed over the 3x squared and reduce it. It's positive. 3 divided by 3 is 1. X cubed divided by x squared is x. I don't really need that one there. I'm just going to leave it there for the sake of representing the coefficient. Then multiply positive 1x times the divisor and write it underneath the dividend. Positive 1x times 3x squared is positive 3x cubed. Positive 1x times positive 0x is positive 0x squared. And positive 1x times positive 1 is positive 1x. And then subtract, which means you switch signs, you change signs and combine. So all of these pluses become minuses. These cancel like they're supposed to. Your x squareds combine to give negative 12x squared, excuse me. Your x's combine to give negative 1x. And then you bring down the next term. When you bring down the last term, you know this is the last go around. Alright, one more time. Leading terms. Divide negative 12x squared by positive 3x squared. Negative 12x squared divided by positive 3x squared is negative 4, because the x's cancel. So my last term of the quotient is negative 4, and now it's time to multiply. Negative 4 times 3x squared is negative 12x squared. I was expecting that. Negative 4 times positive 0x is negative 0x. I only said negative because negative times positive is negative. I know it doesn't matter. And then lastly, negative 4 times positive 1 is negative 4. Change the signs and combine. Don't forget you're subtracting here. So that becomes a plus, that becomes a plus, and that becomes a plus. These cancel. That's what these motions do. They guarantee a canceling here. The x's combine to get negative 1x. The constants combine to get positive 1, positive 4. You're done with the dividing because you're out of terms to bring down, and the way that you know that you're done is that the degree of your remainder is now less than the degree of your divisor. When the degree goes below, it's time to stop, and it's time to write the answer. So the quotient's on top. It's 7x squared plus 1x, I'm not going to write the 1, minus 4. And for the remainder, you literally add the remainder on top of the divisor, which was 3x squared plus 1. I really don't need to write the 0x down here because I have no need for a placeholder. So it's a messy looking answer, but it's the answer nonetheless. Let's see if we got it right. 7x squared plus x, you can see it here, minus 4. And the remainder was negative 1x plus 4. I know I don't need the 1 in negative 1x. I just want to see if it'll accept it. And it does. Good job. Why, thank you. Alright, so long division is called long division for a reason. It's long. But it doesn't take too long for the directions to shift to something called synthetic division. Get very accustomed to synthetic division because the next section relies on it. If you can't do synthetic division, you can't do the next section. So let me throw a new page in here. Add page. Alright. Synthetic division is easy. The problem is you can't always use it. So let me start by telling you when you can use it, or rather when you can't. Synthetic division can only be used if the divisor is x plus some number, we'll call it C, or x minus some number, we'll call it C again. Any variation from that, you can't use synthetic division. We couldn't use synthetic division on the last problem because it was 3x squared. The 3 and the square are bad. We couldn't even use it if it just said 3x plus 1 because the divisor has to have a leading coefficient of 1 and the degree has to be 1. So it's got to be x plus a number, x minus a number. Here's an example of a problem that can use synthetic division. Let's say I ask you to divide. Do not be intimidated about the length of this problem. X to the fourth plus 7x to the third minus 15x plus 9. Now if you, oh wait, divide that by x plus 2. Now if you're thinking, wait a minute, you left out the x squared term. Yes, I did. I did it on purpose so that I can mention what to do if there's a missing pattern again. But it's just like the case in long division, which you'll see here in a second. Alright, here's how you pull off synthetic division. Synthetic division has 3 very distinct parts. The first part is the setup. Before I write the setup, let me kind of describe how the problem is going to look. You're going to have 3 rows of numbers. These arrows are not part of it, they're just for emphasis. And there will be a horizontal line separating the second and third rows. To the left of the top row, you're going to have a box. Here's the setup. The setup has 2 parts. The number that goes in the box, which I call the box number. The box number is the 0 of the divisor. Now we talked about zeros in the previous section, 3.2. Remember, a 0 is a value that turns an expression into 0. So for example, look at x plus 2 and ask yourself, what number would you put here to make this equal 0? And the answer is negative 2. Now what most people eventually settle on is, oh, you just want me to change the sign of this number. Well, yeah, that'll work too. But the number in the box is the 0 of the divisor, or change the sign of the number in the divisor. The purpose of that sign change is to take care of all the sign changes in long division. Like back here, when we had to change all these signs, this one sign change in synthetic division takes care of all that. So you only have to change the sign once. But that's not all of the setup. The second part of the setup is the top row. The top row is the coefficients of the dividend. And this is where you got to know your vocabulary. The dividend is what you're dividing into. In this problem, it's the one that starts with x to the fourth. So you just go across and write your coefficients. For example, in front of the x to the fourth is a 1. In front of the x to the third is a 7. In front of the x to the second is a, wait, there's not an x to the second. And because there's not, I have to use a 0 to represent it. In front of the x is a negative 15. Yes, it's negative. And then the constant term goes last. It's the 9. So the setup's easy. You change the sign of the number in the divisor. That goes in the box. And then you take out the coefficients from the dividend, and that makes the top row. Basically, you're taking all the x's out of the problem. Once you get it set up, your second move in synthetic division is the work. And just like the setup, the work has 2 parts, but I'm going to write A, B, and C. You'll see why. In order to do the work, you now have to look at synthetic division not as rows, but as columns. This synthetic division problem has 5 columns. The box is not considered to be in a column. You start at the left column, or in the first column, if you will. In the first column, you add. And you might be thinking there's not 2 numbers in the first column. You're right. But you can imagine there's a 0 here. 1 plus 0 is 1. Now most people just say drop the first number, and that works. But I'm saying add because that's what all the other columns are going to do. So you add the first column. Your second move is to multiply diagonally by the box number. If I can spell, multiply diagonally by the box number. Here's how that works. After you've added a column, take your sum, and you're going to go this direction. You don't have to draw the arrow. When you go that direction, you multiply by what's in the box. So in this case, 1 times negative 2 is negative 2. When you multiply, you go up a row into the right one column. After you've multiplied diagonally by the box number, your third step is basically to repeat until the last column is added. Repeat until the last column is added. In other words, it's time to add again. Add the second column. This time you actually add and you get 5. And then multiply diagonally by the box number. 5 times negative 2 is negative 10. Add the next column. 0 to negative 10 is negative 10. Then multiply diagonally by the box number. Negative 10 times negative 2 is positive 20. When you multiply, make sure you line up the next column. I see a lot of people misalign it and get thrown off. Add the next column. Negative 15 and 20 is 5. Multiply diagonally by the box number. 5 times negative 2 is negative 10. And finally, add the last column. 9 and negative 10 is negative 1. It may take a little bit to get used to when to add versus when to multiply, but I promise you, synthetic division makes things a million times easier. And I wonder if I should have done this a long time ago to make it a little bit easier to see. Let me check. That's beautiful. I guess, I don't know. Hi. Okay. So anyway, you start synthetic division. I'm sorry, that's not what I was about to say. Synthetic division, the moves are really easy because all you have to do is add, multiply, add, multiply, add, multiply, add, multiply, and then add up the last column. As opposed to long division, where you have to get ready. To do long division, you have to divide the leading coefficient of the divisor into the leading coefficient of the dividend. Write that as the first term of the quotient. Multiply that times the divisor. Write that product underneath the dividend. Change the signs of all the terms. Add. Drop the next term in the divisor. Dividend. And then do it all over again and again until you get to the end. So it's annoying. It's very annoying. As opposed to synthetic division where you add and multiply until you get to the end. But be careful. We're not done with synthetic division. We're doing a polynomial division problem. Remember? It's up there. We started by taking out the x's. We finished by putting them back in. So the third part about synthetic division is how to write the answer. And just like everything else, it has 2 parts. To write the answer to the synthetic division, you put the x's back in, but you don't put them back in the way you took them out. When we took these x's out, they started with x to the 4th. When you divide, the degree goes down by 1. So here's how you build your answer. The first part of the answer is the bottom row. In the bottom row, you put the x's back in, but 1 degree lower. Remember, degree is the highest power. The previous degree was x to the 4th. Now it's going to go in 1 degree lower. I'm going to go and start building the answer and show you what happens. And then I'll tell you part B. So the 1 in the bottom row at the beginning represents 1x cubed. I know I don't need the 1. I'm writing it for emphasis. And then work your way down. The 5 represents plus 5x squared. And then the minus 10 represents minus 10x. And then the 5 represents plus 5. What should happen is you should run out of x's right before you get to the last number. And the reason is the last number is the remainder. And that's part B. Last number equals the remainder. And we're going to write the remainder the same way we did before. Literally add the remainder on top of the original divisor, which I believe was x plus 2. And you're done. It may look like it takes a long time. No, it takes a little while to get accustomed to. But once you get synthetic division down, it flows so smooth it's not even funny. A couple of comments about this answer. I don't need the 1 in front. I could have just put x cubed. But another more subtle thing is I just added a negative over here on the fraction, so I could have just as easily written minus 1 over x plus 2. Because plus and negative is redundant when you can just say minus. But that's synthetic division. I want to do one more synthetic division problem before I show you how it's used, because I do want to show you how efficient it is. Excuse me. For example, go back in black for a second. For example, let's say I ask you to divide the following. X to the 5th plus 32 by, I don't want to use the same divisor again. Oh, I will use x minus 2. Ooh, now it's a minus 2. Alright, careful. This is missing a lot. Not in the divisor. The divisor is what it is. You change the sign of the number. So the box number is going to be positive 2. Remember, to make the box, you change the sign on the divisor. What's missing a lot of powers is the dividend. It starts with an x to the 5th, and then there's no more x's. Well, there's one x to the 5th, so I got to start with a 1, and now keep track of each power. 1x to the 5th, no x to the 4th power, no x to the 3rd power, no x to the 2nd power, no x to the 1st power, and finally, the constant term at the end. Now, in a situation like this where you have a lot of missing powers, it might be beneficial to use the following gimmick. It's not necessary though. This first column represents x to the 5th. Then just write each successive power, and then the last one is your constant. This way you can keep track of who's missing and how many zeros to put in the top row. Now, how fast does synthetic division go? Well, since you can watch this over and over again, I'm going to do it at the normal speed that I would do if I were working this problem on my own. And then you can step back and go nerd. Alright, remember, every time you go down you add, every time you go diagonally you multiply. So in this problem it's times 2. So here we go. Add to get 1, 1 times 2 is 2. Add to get 2, multiply by 2 to get 4. Add to get 4, multiply by 2 to get 8. Add to get 8, multiply by 2 to get 16. Add to get 16, multiply by 2 to get 32. Add to get 64. Add, multiply, all the way across. Oh, a gimmick I forgot to mention earlier. If you forget when to add and multiply, here's a visual gimmick. When you go this direction, that's half of the plus sign. So when you go down, it's time to add. When you go this direction, that's half of the times sign. So when you go diagonally, it's time to multiply. Just a little gimmick to help you remember. Careful, problem's not over there. I have to put the x's back in. They go in 1 degree less. My original problem started with x to the 5th, which means my answer starts with x to the 4th. 1x to the 4th, plus 2x to the 3rd, plus 4x squared, plus 8x, plus 16. Oops, ran out of x's, but you're supposed to, because the last number is your remainder, and it goes on top of your divisor. So all of that would be your answer. Wait a minute, that's not missing any pieces. Well, no. Doesn't mean, just because they were missing in the dividend doesn't mean they're going to be missing in the quotient. Remember, they're not really missing, they're just represented with a 0. They just have different coefficients now. Okay, so synthetic division. Let's pretend that you practiced it enough to get this flow down pretty quickly, where you can set it up, knock it out, and then build your answer. Why are we even bothering? Well, let's do the homework, go through the homework and see if we can figure out where this plays out in context. Divide using synthetic division, divide, careful, this is missing 3 powers, 5th, 3rd, and 1st, so it'll have 3 zeros in the setup. This one is missing x to the 4th and x squared and x, so you would have 3 zeros on the top. Hey, didn't know that was there. No, really, I didn't. I just made it up. Whoa, this has more words. Use synthetic division to divide. Use the result to find all zeros of f. Now, wait a minute. I remember what zeros meant. 0 means the things that make this equal to 0. And you find them by putting this equal to 0 and solving it. How would you do that? By factoring it. So what does division have to do with factoring? Well, I'll show you, but first let's do the synthetic division problem. So give me a second to get it set up. I got enough room on this page to do this whole problem. Alright, so let's see. If f of x equals x cubed minus 13x squared plus 47x, oh get a jump for me, minus 35, find the zeros. Yeah, you jumped again. Find the zeros of f of x. Start by dividing f of x by x minus 1. And yes, I am taking some liberties in rewording this problem, but this is the gist of it. Find the zeros. By the way, start by doing this division problem. And I'll admit that in general, when you're finding zeros of a function, you're not going to be told what to divide it by. But let's say that you are. As a division problem, the box number is the opposite of the number in the divisor. So the box number here would be a positive 1. There's no missing terms in the function, so I can just write my coefficients. 1x cubed minus 13x squared plus 47x minus 35. And of all the box numbers, 1 is the best. Because with the exception of 0, 1 is the easiest number to multiply by. All I got to do is remember when to add and when to multiply. Here we go. Add the first column to get 1, multiply by the box to get 1. Add to get negative 12, multiply by the box to get negative 12. Add to get 35, multiply by the box to get 35, and look what happens when I add these. I get a remainder of 0. Why does that matter? Well, you'll see why in just a second. As a division problem, here's what I know. I know that this function divided by x minus 1 equals, remember the degree goes down by 1, so it starts with 1x squared minus 12x plus 35. Now, how does that help me? Here's how. If you have a division problem with a remainder of 0, we'll call this an FYI. If you have a division problem with a remainder of 0, for example, a divided by b equals c, for the sake of being generic, that's the same as the following multiplication problem. If you take the c and multiply it times the b, you get back a. Real quick number example, because I know letters kind of cloud the issue sometimes. If I say something like 18 divided by 6 equals 3, and I ask you how to check it, you could say 3 times 6 equals 18. So if you have a division problem with a remainder of 0, you can turn the division problem back into a multiplication problem. How does that help us here? Here's how. We have a division problem with a remainder of 0. We can turn it back into a multiplication problem by taking the quotient, which was x squared minus 12x plus 35, times the divisor, which is here in the division problem. The divisor here was x minus 1. And that's equal to the quotient, which is the first part of the division problem over here. I'm sorry, that's equal to the dividend. Wrong word. Well, either way, it's f of x. Look what I just did. Here's my function unfactored. Here it is partially factored. If I'm going to put this equal to 0 and solve it, I need to get it factored. Let me rewrite it with the f of x on the left and the x minus 1 first. Really doesn't matter what order you write it in, since it's multiplied. Something's funny over there. But if I'm going to solve this equal to 0, I've got it partially factored. And if you're observant and your factoring skills are sharp, you know how to factor the remaining quadratic factor over here. Because it starts with an x squared, I can just drop a couple of x's. I need two numbers that add to give negative 12 and multiply to give 35. How about minus 5 and minus 7? Now, I don't have the zeros yet, but notice that I have this factored. I'm going to copy this over to the next page and steal it. I'm going to steal my own creation. Add a page and continue this problem. Oops, I'll move this up here. I got to do that. I'll look and paste it wherever I want. Alright. Remember, we're finding the zeros of this function, which means that we have to solve this thing equal to 0. It's easy now, it's factored. 1, 0 is 1, 1, 0 is 5, and 1, 0 is 7. So why are we doing synthetic division? Because if you have a division problem with the remainder of 0, you get two factors of your function. What you divided by and what you got for the answer. Let me say that again, because that's the key component of what we're doing. If you do a synthetic division problem and get a remainder of 0, your original function just got factored into the divisor times the quotient. And if you're solving an equation and you need to get it factored, that's kind of convenient. Let me go back over here and put in my answers. Wait, it's asking for the answer to the division problem. X squared minus 12x plus 35. Thank you very much. Now it's asking for the zeros, 1, 5, 7. So synthetic division is a tool for getting things factored, which subsequently is a tool for finding zeros of functions, or more generically, solving equations. Wait, that's the only question that says to do that? That was stupid of me. Don't worry, there's more in 3.4. Alright, so if you get a remainder of 0, awesome. Now you might be thinking, wait a minute, how do you know what to divide by in general? That's 3.4. But the rest of these, there's another one like it. Okay. We'll get to those ones I skipped in just a moment. Solve the equation given that 2 is a 0 of that function. 1, 2, negative 5, negative 6. Let me write the function down. One, 2, negative 5. I forget what the last number was. Negative 6. Alright, so we're given this and we're being told that 2 is a 0 of f of x. And remember what that means is, in other words, we're being told that if we plug in 2 we get 0. And we're being asked to solve x cubed plus 2x squared minus 5x minus 6 equals 0. Well, if you think about it, they just told us one answer. If you plug in 2, you get 0. I'm looking for the numbers that when I plug in, I get 0. Hey, you told me one of my answers. I'm expecting a couple more, because remember, the degree is the most number of answers you can get. Now, how do we get the other answers? Well, here's the trick to how to get the other answers. Here's the key thing that you need to know. The following are equivalent. And what that means is they're all true at the same time, or they're all false at the same time. Thing number 1, x equals a number is a 0 of f of x. I was just told that. I was told x equals 2 is a 0. Number 2, f of that number, f of c, equals 0. That's actually the definition of being a 0. So these two are equivalent because they're definition. But the third thing that's not as obvious is that x minus that number is a factor of your function. And you're thinking, wait a minute, why do you get to say that? Well, look right above. This factor became that 0. So where did that 0 come from? That factor with an opposite sign. This factor became this 0. So in reverse, this 0 came from that factor. In other words, when you put the 0 back into the factor it came from, it changes signs. And that's all this is saying. If you know the 0 and put it back into the factor, just change the sign. Now, why does this matter? Because in this problem, we're being told 2 is a 0. And since these statements are equivalent, when you tell me a 0, you're telling me a factor. So I already know one of my factors. So here's how this problem concludes. Answer. Since x equals 2 is a 0 of f of x, then x minus a factor of f of x. So what can I do with that? Well, think about what it means to be a factor. To be a factor means that you divide into it evenly with the remainder of 0. When you know a factor, start dividing. We're going to divide this function by x minus 2 and see what happens. I think I have room here to finish the problem. If I'm dividing by x minus 2, then my box number would be positive 2. My function was 1x cubed plus 2x squared minus 5x minus 6. Let me double check that. Yeah. Alright, let's go through the synthetic division. Add to get 1, multiply by the box to get 2. Add to get 4, multiply by the box to get 8. Add to get 3, multiply by the box to get 6. Add to get 0. And honestly, I was expecting that. I knew it was a factor, so I knew it divided and gave a remainder of 0. So here's what I know about my function. When you get a remainder of 0, and you will frequently see me turn that 0 into a smiley face, you'll see why in 3.4. You have two factors. One is what you divided by, which is the x minus 2. The other factor comes from the quotient, which is on the bottom row. Just remember to go down 1 degree. This started with x to the third, which means the quotient starts with x squared. 1x squared plus 4x plus 3. It's not completely factored, but the minute you get it down to a quadratic factor, the one that starts with x squared, you can either try to factor it further, manually, or honestly, just get out the quadratic formula on it. But if these factor, the quadratic formula is a little overkill. This does factor in x plus 1 and x plus 3. And now that it factors, I know what my 3 zeros are. 1 0 is x equals 2. Remember the equivalence. If you're a factor, the opposite of u is a 0. Another 0 is x equals negative 1. And the third 0 is x equals negative 3. So, that's what synthetic division gets you. If you're solving an equation equal to 0, if you're finding zeros of a function, and you know one factor or 1 0, you can set up a synthetic division problem to get the factoring started and perhaps finish the factoring manually. Alright, let's take a look at one more issue in here, and that'll be the end of this lesson, and then I'll make another video for 3.4. I want to go back to, that's more of the same, don't let the fractions scare you, just do what you would normally do and you'll be okay. Or click do an example. But I want to go back to one of these that says